In the last video, I explained how to construct a topographic profile from a topographic map. In this video, I'm going to show you how you can create the topographic map itself, as well as go over an example that might help you make the connection between topographic maps and engineering. So in order to make a topographic map, first we need measurements. And the way these measurements are taken is you go out into the field with a GPS and an altimeter in an area where you want to make a map, and you walk up and down all the hills and look for outcrops of rock, or maybe rivers or other features like that. And then when you find one of these features, you record the information in your notebook and then come back to the lab or your computer and plot it on a base map of the area using those GPS coordinates. And when you're done plotting, you'll get something that looks like this. So here we have a map, and it's got some measurements taken at maybe some outcrops, and each point relates to the height above sea level at that location. Now remember, before we draw out our map, there are a set of rules that we need to adhere to. So these are those rules that you must follow when constructing a topographic or contour map. Every point on the same contour line has the same elevation. A contour line always rejoins itself to form a loop, and this might happen outside the map area. Contours usually encircle a hilltop. Slopes rise or fall at right angles to the contour line, and closely spaced contours indicate a steep slope, whereas further apart contours might indicate a gentle slope. And evenly spaced contours might indicate a uniform slope. Contour lines never merge, split, or cross one another. And contour lines always bend upstream, forming a V when they cross a river. Okay, so with that information, let's draw our contour map. But first we need to decide on a contour interval. And I'm seeing some points here in the 20s, 30s, 40s. So let's go with a contour interval of 10 meters. That should keep it from looking too messy. So a good way to get started is by starting at the 0 meter interval. And you might be saying, wait, what? There's no zeros on this map. Maybe he means we should start at the closest number to 0, which is a common mistake. There actually is a 0 meter contour shown on this map. Remember, we base the elevation off of sea level. So this line right here at the bottom is the 0 meter contour. Okay, so one down. The next one we would plot would probably be the 10 meter contour, and that's fairly easy. Now you can see here that we have a 9 meter mark and a 14 meter mark, but there's no 10 in this area on the left side of the river here. Now, why is that? Well, it's because these measurements were taken in the field at different outcrops. So there isn't always going to be a rock sticking out with an elevation of exactly 10 meters. So we have to estimate. So the 10 meter contour would go between these 2 points. And we know that 9 is closer to 10 than 14 is, so the line would probably be more toward that side. So we can start drawing our line in, and maybe it looks something like this, but now we're approaching the river, and what do we know about rivers? Well, when a contour line crosses a river, it forms a concentric V pointing upstream. So it might be something like this, and then come down here, and we can see the 10 meter line, so we'll cross that directly, and then just above the 9 again, through here, and off the screen. So that would be our 10 meter contour line. And it's important to note that your map might not be exactly accurate to what it would be in the field. It's merely an educated estimation based on the limited point measurements that were taken. Okay, so the next one would be the 20 meter contour, and similarly we would start over here, and look, we've got a nice 20 there, so let's cross the river, come down through the 20, through the 16 and 24. But now we're getting to something a little strange here. I see a 15, a 12, and then a 43 with no points in between that are in the 20s and 30s. So it's a little confusing. But look at all these points around here. These are all in the 40s, and then we've got some lower points all around. Okay, so let's just take a break from that area, and we'll come back to it in a little bit. So the next line would be the 30 meter contour interval, and again, that's fairly easy. We've got a nice 28 here on the left, so our line would be fairly close to that. It's going to be underneath that 33 there. It's going to go up the river, and then down, and then thread the needle between these 2 points. But then we get to here, and I see a 27, and I see a 30 over here. So we can't just cut across, because that wouldn't make sense, because then this 27 here would be on the wrong side of the interval. So then what we could do is we could go up around this 27, right? And then we could go down to this 30. Now we've got a 32 there, but we want to make sure we stay on the right side of it. So we obviously wouldn't go between the 30s and the 40s, right? So we're going to go on this side of the 32, and then we've got this 28 here that we've got to avoid. And then we've got a 31 down here. And now we're back to our confusing area from the 20-meter contour line. But if we were to just make a run for it and go, through these numbers here, that still makes sense. But now it starts to fall apart because there are no other 30 points in this area. Now you might think we can just go up here and, there we've got a circle and they connect. But if you remember, one of the rules stated that contour lines never merge, split, or cross one another. So that doesn't work. We can't do that. So what I'll do is I'll just erase that line. We'll go back a little bit, and let's reassess. We'll try something a little easier. It looks like there's a bunch of outcrops here in this circle that are above the 40-meter contour. So why don't we just draw that line in? So we can start it here, and then it would kind of go around these numbers, and the line is encompassing all of these numbers that are above 40. So that one looks pretty good. And now if we look at this, it's almost a circle, and we know that from our rules that contours often encircle a hilltop. So if we have the 40-meter contour here, maybe then we can add the 30-meter contour line as well around the same hill, right? Because if you were walking up the hill from the shoreline, you would hit the 20, then the 30, then the 40-meter contour, right? So let's add in the 30, and we can do that fairly easily here because we have a point that's right on 30. So we'll do it the same way we did last time, and we'll go on this side of the 32 and the 36, but then on this side of the 28, and then again on this side of the 31. And now we get to this area that gave us trouble with the 20-meter contour line. But if I continue around the hill, what I can find is that we can connect to here, and then the 20-meter contour line, we can finish that off by just kind of sending it down here in between all these points and then off the page, same as we did with the 10-meter line. And these lines are fairly close together, but of course they don't ever cross. And that would suggest that we have a very steep slope on the south side of the hill here. And then finally over here in the northwest corner, we have a few more points in the 40s. So there would be another 40-meter contour line over here, right? So it would be below this 41, up at the river, and then down below the 42. And we see the same issue we had with the 30-meter contour line over here. It doesn't really have anywhere to go. So what we can do in this situation is we can just send it off the map like that. Okay? So that's it. The contour map is done. And you might be thinking, well, why are there two 30-meter and two 40-meter contour intervals? How can they just go off the map like that? But remember that the contour interval is only a representative of that exact elevation. So everything in between the contour interval is in between the two lines. So this is a 30-meter contour interval over here, and this is also a 30-meter contour interval. And all that means is that everything in between has to be above 20 meters, but below 30 meters, okay? So all the points in here, we can see 28, 23, 24, 26, 23, 27, and then even 28 all the way over here. They all lie below the 30-meter contour interval, but above the 20-meter contour interval. So our map makes sense. So the last thing you would do is you would write in the numbers. So we had the 40-meter there, we had another 40-meter here, we had the 20-meter, and we had the 10-meter, and of course the 0-meter, which you may or may not write in. And now we're finished. But you still might be wondering, okay, why did those two contour intervals go off the map? Why didn't the 30 just connect over here and then maybe, it went like this or something like this? How can I be sure that it went off the map? And to be honest, you can't really be sure that the contour interval just goes off the map. But what you have to remember is that the map that you are drawing your contour intervals on is only a small area. And unless it's a map of an island, there are always going to be places out of the extent that you have. But what if we were to zoom out, use a different scale? We might see something like this, right? So if I recreate that map, we've got the same river there, but if I recreate the hilltop, over here, that was the 40-meter contour interval, and then the 30-meter, something like that, and then we had the 10-meter, down here, and the 20-meter, this is obviously not the right scale, and then we had another 30-meter contour interval up here, and I said it just kind of went off the map with the 40, right? So that was our extent previously, but maybe those two contour intervals circled around, this lake here and formed another hilltop. And that hill had a lake on it, and the lake was feeding the river and flowing down through our map. But based on the points we had and the extent of our map, we just don't know what's going on up there, and that's okay. All we were tasked with was mapping this smaller area down in this quadrant here, okay? So that's it. That's how we make topographic or contour maps. And you could then take this map that you just made and make a topographic profile like we discussed in the previous video. But it's important to note that these maps also have engineering implications, right? You might need to use this information for some sort of an engineering project. It's obviously important to know about the area you're working in, but elevation data is also useful when citing new projects. So what comes to mind for me is a hydroelectric power generating station, right, like a dam. It should be obvious that you would need to know the elevation of rocks that are going to surround the reservoir, and citing areas that will make good dams is definitely important. But most rivers are already dammed if they can be, so you might not end up doing that as part of your career. But a similar kind of structure, and something that also provides us with electricity, is what's called a pumped storage or pumped hydroelectric generating station. And what a pumped hydro plant is it's kind of like a big battery that we can use to store energy for times when we need it. Now, energy production is fairly stable when we use fossil fuels, but moving forward to a greener future, we are trying to reduce our dependence on such resources. Obviously, renewables like wind and solar are good alternatives, but they can be intermittent, right? So if it's not windy one day or it's nighttime, solar's not going to work. But if we had a way to store excess energy these sources produce and then tap it later, that would go a long way toward reducing our dependence on fossil fuels. So a very basic diagram of how pumped hydro works is shown here. We have two reservoirs, and right now the bottom one is full and the top one is empty. We also see a couple of windmills here representing our renewables. So we can use the excess power they generate to pump water from the lower reservoir to the higher reservoir. And as this happens, it's essentially charging our battery. So now the sun has gone down and the wind is slowed, but the town is still hungry for electricity. So what we can do is run the system in reverse. And as the water flows back through the turbine, it generates electricity in the same way that a normal hydroelectric dam generates electricity. But this system can only last for so long before the upper reservoir is empty again, in essence meaning our battery would then be dead. But this is a good way to supplement renewables. Now, what does this have to do with topographic maps? Well, finding suitable sites for pumped storage is very difficult, and this is because we need two storage reservoirs located close together, which is hard enough, but these also need to be separated by an elevation of several hundred meters to allow for enough potential energy to be stored. While at the same time, the horizontal distance between the two reservoirs needs to be fairly short to prevent energy from being lost to friction. So suitable locations are not all that easy to find, and it becomes even more difficult when you factor in the environmental concerns that come along with any big reservoir, as obviously the flooding causes lots of problems. But let's take a look at our map and see if there might be a good location that we could install one of these generating stations. Okay, so right away I can see that our hill isn't quite tall enough, but maybe if instead of this hill being 40 meters tall, it was 400 meters tall, we could put our upper reservoir on this hilltop here. It's fairly flat, and then we could put our lower reservoir down here. And the steep slope in between the two reservoirs would likely fit the parameters of our project. So hopefully this video helps you with your assignment on topographic mapping. but also to understand why this might be a useful concept for engineers to understand.